Welcome to Tech Bytes in News, your daily roundup of articles featured in Hacker News. Today, we're diving deep into the fascinating world of compression algorithms. It's a topic brimming with clever techniques and surprising efficiency.
I'm really excited. So what are the main types of compression we'll be discussing?
Primarily, we'll focus on lossless compression, where the original data is perfectly reconstructible. We'll touch upon lossy methods like JPEG briefly, but the core of our discussion will be algorithms that preserve all information. Think of it as squeezing a sponge. You want to get it as small as possible, but you still need to be able to restore it to its original shape and size.
Got it. And what are some of the key algorithms we'll be exploring?
We'll cover several, starting with the simpler ones like run-length encoding, RLE, which is great for consecutive repeating data. Then we'll move on to more sophisticated methods. Lempel-Ziv, LZ, Huffman coding, and the algorithms built upon them, such as deflate, used in gzip, zip, and PNG, snappy, LZ4, and ZSTD. Each has its own strengths and weaknesses in terms of compression ratio and speed.
So deflate, that's the workhorse behind gzip, right? I've always wondered how it works.
Exactly. Deflate cleverly combines LZ77, which identifies repeating sequences and replaces them with pointers, and Huffman coding, which assigns shorter codes to more frequent symbols. It's a beautiful example of synergy. The author mentions a hilarious anecdote about the developers experiencing cabin fever while working on the bit-level hacks. It really highlights the complexity involved.
That's amazing. And what about Snappy? I've heard it's incredibly fast.
Snappy prioritizes speed over maximum compression. It uses a simpler approach than deflate, focusing on finding the most recent matching sequence, rather than maintaining a complex chain of potential matches. This makes it blazing fast, but at the cost of a slightly lower compression ratio. The author even mentions its previous name, Zippy, which brings back some fun memories.
Interesting. So LZ4 and ZSTD, are they similar to Snappy?
Yes, they're also LZ-based, but they offer improvements. LZ4 is faster than Snappy with comparable compression ratios, and ZSTD, its successor, aims for a balance between speed and compression ratio, often outperforming deflate in both aspects. It's a real game changer.
Wow, that's impressive. The article also mentions arithmetic coding and FSE. Are those crucial for understanding ZSTD?
Yes, they are. Huffman coding, while efficient, has limitations. Arithmetic coding addresses these by assigning bit lengths proportionally to symbol probabilities, but it's computationally expensive. FSE, finite state entropy, is a more efficient alternative used in ZSTD, offering a good compromise between compression ratio and speed.
So it's all about finding the right balance between speed and compression, right? Different algorithms excel in different scenarios.
Precisely. The choice of algorithm depends on the specific application. If speed is paramount, Snappy or LZ4 might be preferred. If you need maximum compression, deflate or ZSTD are better choices. And ZSTD's ability to use trained dictionaries is a significant advantage for compressing specific data types. It's a fascinating interplay of trade-offs.
I see. This has been a really insightful discussion. Thanks for breaking down these complex algorithms in such a clear and engaging way.
My pleasure. It's a truly fascinating field, and I hope this gives our listeners a better understanding of the magic behind data compression. Remember to check out the original article for even more details. And that's all the time we have for today's Tech Bytes and News. Thanks for listening, and have a great day.
Bye-bye.